greetings. We will discuss the unit 4 in this course, and this will be on the dynamical symmetry in the Kepler problem. We will have a continued discussion on symmetry and conservation laws with a specific reference to the dynamical symmetry in the Kepler problem. Now, for those of you who joined the course late, let me mention that in unit 1 we studied the equations of motion, the Newton, Lagrange and the Hamilton's equations of motion, and then we studied the oscillators, and we studied the polar coordinate systems in unit 3, and we will be using the polar coordinates in today's class. We have already had some acquaintance with the connection between symmetry and conservation laws, which we met in the first unit, where we illustrated this in a few cases, and this unit number 4 is specifically designed to discuss the dynamical symmetry, the so called dynamical symmetry, or it is also called as the accidental symmetry in the two body Kepler problem. Now, first we will recapitulate a little bit the connections between conservation and symmetry and associate conservation of energy with symmetry with regard to temporal evolutions. So, we will very quickly recapitulate this, but we will see it coming in a slightly different context than what we have seen earlier. And specifically what we will do is to find how to determine what physical quantities are conserved if you know what the equation of motion is. So, given an equation of motion, how do you get a conservation law? Okay, so that is something that we will discuss. So, just as conservation of energy comes from the symmetry with respect to temporal evolution over a passage of time, the conservation of angular momentum is connected with the central symmetry, and we will also get this from the equation of motion. And then we will ask that in the Kepler problem you have these elliptic orbits that you see, and sure enough this solution is quite correct, but why does the ellipse not precess? Why does it not go from one to the other in what is called as a rosette motion? Because if you look at this from a distance, it will look like the petals of a rose, and it turns out that neither the conservation of energy nor the conservation of angular momentum is sufficient to explain the fact that the ellipse does not actually precess and the ellipse does not undergo a rosette motion. So, we will try to understand what is the origin of the fact that the ellipse itself is fixed, it does not precess. And this is connected to what is known as the dynamical symmetry of the Kepler problem, and there is a vector quantity which is conserved, which is along the major axis of the ellipse. So, that remains fixed. This vector is called as the LRL vector or the Laplace-Runge-Lenz Vector, and we will study this. And the motivation to study this topic is to explore further the connections between symmetry and conservation laws, because this has got very important and deep consequences on the very foundations of physics, the very frontiers of physics, and also on technology, because we need to study the mechanics of flights in space, and all of these things have to come together when it comes to the rocket technology, for example. And this is particularly important for us because we are now in the space age, and there are many scientists, engineers, technologists, entrepreneurs amongst you. These are the people behind the rocket science technology. The Russian, however you pronounce it, the first name sounds a little easier, which is Konstantin, followed by a family name, and then Robert Goddard, the American, and Hermann Orbit, who was a German, and these are some of the first pioneers of the rocket technology. And in our own context, of course, we have Dr. Vikram Sarabhai, who is regarded as the father of India's space program, and this is especially important for us. The ISRO has a large number of space related projects in which we fire rockets and satellites into space, and it is obviously very important both for fundamental physics as well as for high end technology that we study these topics in some details. Now, of course, gravity plays the most important role in all of this. So, we will begin our discussion with the two body Kepler problem, in which the two bodies have a gravitational interaction between them, and then of course as one studies this subject further, one will need to adapt the formalism to study satellite orbits and other things. We begin this discussion by raising a question that in the Kepler problem, other than the energy and angular momentum, what else is conserved? Is there anything else which is conserved in addition to energy and angular momentum? We also ask the question that for a given physical law of nature, if you know the law of nature, if you know what is the physical law, then given this law, can you determine what quantities will be conserved, and how do you determine this? What is the mechanism of discovering the conserved quantities if the law of nature, the physical law, is already known? We can also ask the inverse question, that if you observe what physical quantities are conserved, then from this can you deduce what the law of nature is, okay, which is the inverse question. Means ultimately one of the major goals of physics is to discover the laws of nature, and you could propose it, you could discover it through observations, and then use the laws of nature to find what physical quantities will be conserved, or ask an inverse question that from the observations about the conservation of physical quantities, how do you get a law of nature? So, we will discuss some of these issues in this unit. So, we begin by asking this question: how did Kepler deduce that planetary orbits are ellipses around the sun? And I think looking at this Kepler's picture, what bothers me more is not quite why and how the planetary orbits go around the sun, but why this piece goes around his neck, and this is something which bothered me, and it worries me about Kepler, even if I know that he died in 1630. But this is the question, and I think you can try to answer it first by asking yourself, how would you find what is the trajectory of a planet if it is known that the interaction between the planet and the sun is given by the law of gravity, which is g m1 m2 by r square, that is the force of attraction between two masses. So, how would you solve this problem? And I would think that what you might do is set up the equation of motion, right, which is F equal to ma. You know F, which is g m1 m2 by r square, and you know the force, the magnitude and the direction, and you have a differential equation. So, you will solve it, and from the solution of the differential equation you will get the trajectory. That is how you will solve it. Now, Kepler did not know differential equations, and Kepler did not know that the force of attraction between two masses is g m1 m2 by r square, and that is the reason the question that is raised at the top of this slide is, how did Kepler deduce that planetary orbits are ellipses around the sun? So, obviously, he did not use the technique which you would use today. What Kepler did was to make use of observations which were tabulated by Tycho Brahe. Tycho Brahe was a brilliant astronomer, and he recorded the positions of various planets and how these positions change with time over a course of a year. And from these positions, what Kepler did was to do very clever curve fitting, and he deduced that if the positions of the planets have to be what they were reported in Tycho Brahe's very careful observations, then the orbits will have to be ellipses. Now, this was a conclusion he sort of deduced on the basis of very accurate and careful observations recorded by Tycho Brahe. Now, Tycho Brahe was a very brilliant astronomer. He was from Denmark originally, and he had in fact his own Tychonian model of the planetary motion. We mentioned the Copernican system, the Ptolemy system in one of our earlier units, and what Brahe did was to come up with a planetary system which was his own, in which he presumed that the planets go around the sun, but then he had the sun and moon go around the earth just like Ptolemy's system. So, it was a combination of the Copernican and the Ptolemy system. And although this has nothing to do with the topic, it is something which I thought I will ask you if you are aware what Tycho Brahe's nose was made of, and maybe some of you know the answer, and it was made of gold. And the reason it was made of gold is because he lost it in a sword duel with another student, and they wanted to decide between them as to who was a better mathematician. And I am sure you are very competitive, but please use some other ways of settling who is a better mathematician. He discovered the supernova in 1572 in the constellation Cassiopeia, and Kepler of course needed access to Brahe's observations, because it was by doing clever curve fitting to Tycho Brahe's data that Kepler finally got the ellipse. But it was not easy, because Brahe would refuse to share his data with Kepler. He was very possessive of his data, he did not want to share it with anybody. They quarreled, and only on Tycho Brahe's deathbed that he finally gave his data to Kepler, saying that let me not seem to have died, to have lived in vain. And saying this, he finally handed over the data to Kepler, and then Kepler was able to deduce that the planetary trajectories will have to be ellipses. Now, the solution that that you would get by solving the differential equation and plugging f equal to g m1 m2 by r square would also be correct, and this is dynamics, but this came well after Kepler, and it came through the developments and the development of equations of motion through Galileo's law of inertia, followed by Newton's laws of motion. But then it also required the knowledge of gravity, and this is something for which the two body problem has to be solved. So, let us quickly go through this. So, you have two masses m1 and m2, and these are referred to some coordinate system over here, and with respect to this coordinate system you have the respective position vectors r1 and r2. You have got a relative difference vector which is r2 minus r1, and then there is a direction which is the line along which the interaction between m1 and m2 take place, and this direction is given by this unit vector r vector divided by its length. So, you get only a direction. So, the force by the mass 1 on the mass 2 is given by this, which is mass times acceleration, this is the force, and this is gravity g m1 m2 by r square, and likewise the force by 2 on 1 is again mass times acceleration for the object 1, and I have defined the unit vector along the direction in which I have shown from m1 m2 m2, which is why this force is along plus u, whereas this force is along minus u, because they are toward each other. It is also useful to find the center of mass, which is given by the weighted position vectors weighted by their respective masses. So, you define a center of mass which is in between and closer to the larger mass, and we develop an approximation when one of the masses is much larger than the other, which is of course true for the solar system, for any planet in the solar system, or for any satellite of any planet in the solar system. So, it holds good also for the moon and the earth system, or of course for artificial satellites which you will launch in due course of time. So, this is the basic algebra which defines the center of mass coordinate system. There is nothing very special about it, and from this you can get an expression for the acceleration. So, you can develop an equation of motion for the planet in the field of the center of mass by determining what its acceleration is, which is, since this relative coordinate is just the difference of these two position vectors, its second derivative will give you the corresponding accelerations, and from these two equations you can just subtract this r1 double dot from r2 double dot and get the equation of motion, right. So, this is a very simple straightforward equation of motion. This has got a magnitude of the distance between the two, this is the cube of the distance. So, essentially you are getting an inverse square law force. So, this is your equation of motion, and from this equation of motion you can get the solutions. How will you get the orbit? You have to solve the differential equation, and from the solution of the differential equation you will get the actual trajectory, the orbit. We have set it up under the assumption that one of the two masses is much larger than the other, which is a perfectly good approximation in the context in which we are discussing this. Notice that the constant kappa, which is determined by the universal constant g and the two masses, which is approximated to g times m1, because m1 is much larger than m2. So, this is the constant, it is determined completely by the universal constant and the mass of the object 1. This has got the dimensions of L cube t to the minus 2, and keep track of this, because in some books and papers you will find that some other units have been used, and sometimes these terms have been scaled by some other mass constants. So, you may see a slightly different expression than what you will see in this class. So, kappa has got the dimensions of L cube t to the minus 2. Now, this is the equation of motion, and what we will now do is to take the dot product of the equation of motion with velocity. Okay. Now, why do we do that? What you are going to learn, that by playing with the equation of motion, okay, by carrying out simple straightforward algebra, you can actually discover what physical quantities are conserved. Okay, so, you do not have to learn conservation principles as a different postulate or something, but they come from the equation of motion. Given the law of nature, you can find what physical quantities will be conserved. And then of course you could ask the inverse question, that if you know what physical quantities are conserved, can you get the law of nature. Okay. So we will first acquaint ourselves or reacquaint ourselves with how you get the law, the conserved quantities from the laws of nature. So the law of nature is built into the equation of motion, because we have plugged in the gravitational law. That is the law of nature that we have plugged in. Okay. There is a physical law that we have invoked, we have plugged it in, and from that we get the equation of motion. And what we do now is to play with this equation of motion. So what we do is to write the equation of motion and compose the scalar product or the dot product of the velocity with the equation of motion. So this is exactly what we have done. We have this equation of motion, take the projection of this on the velocity. So it is r dot dot r double dot. So this is the scalar product. Likewise this is r dot dot r from the second term, and on the right hand side you will of course get the number 0, right. So this is the dot product of the velocity vector with the equation of motion. Now we know what the velocity is. The velocity is the time derivative of the position vector, and the position vector has got the magnitude and the direction of the position vector, but the direction of the position vector is not a constant quantity. So you must take into account the time derivative of the direction, which is u dot. So u is the unit vector giving the direction, and its time derivative, which is indicated by u dot, is the rate of change of the unit vector. So we will need this when we deal with the velocity. So now we have this term r dot dot r, which is a scalar product of velocity and the position vector, and this you can easily see is nothing but r r dot. Of course you will need the dot product of u dot with u, but we have already discussed this when we studied the plane polar or the cylindrical polar or the spherical polar coordinate system, that the changes in the unit vectors which change will always be orthogonal to the unit vector itself, which is why it is a change at all. Okay. Otherwise if it has got a component, how would that be a change, right. And we have shown this explicitly in the case of the polar unit vectors, which do change from point to point. So this scalar product is given by the product of these two scalars r and r dot. Likewise we need this one also, and this one is the scalar product. This is velocity and this is the rate of change of velocity, which is acceleration. So this is the scalar product of the velocity with acceleration, and just as in this case this turns out to be r r dot, this will turn out to be v v dot for exactly the same reason. So now you have got a rather simpler form, and you can rewrite this to get v v dot for the first term and the kappa over r cube times r r dot for the second term, and this has come straight out of the equation of motion by taking its projection on the velocity. Now what do you get out of it is an extremely important quantity in physics, because you will recognize that v v dot is v times this derivative of velocity with respect to time, right. And on the right hand side I have moved this term to the right with a minus sign. So r r dot over r cube, so this I have got r over r square, r over r cube gives me 1 over r square, and then I have r dot, which is delta r by delta t, and I must take the limit as delta t going to 0. So having gotten this, if you now integrate this equation with respect to time, you easily get that the integral of the left hand side is v square over 2 and the integral of the right hand side is kappa over r. Okay, it is straight one step integration, and of course there will be a constant of integration, and I merge the two constants of integration coming from integration of this and a integration of this into a single constant of integration which I have written as E. Okay. Now this is an amazing quantity, because what you have discovered from this is the conservation of energy, right. This is a constant of integration, it is a constant and therefore a conserved quantity. We have got this E by integrating this quantity over here. If you differentiate this, you go back to this, these are inverse processes. The dimensions of E come from the dimensions of that we have chosen for kappa, which is L square T to the minus 2. The dimension of energy that we normally talk about is, it also has got a mass, right. So ml square T to the minus 2 are the usual dimensions of energy. Here I have written the dimensions of energy as L square T to the minus 2, because this is what I will be calling as the specific energy, energy per unit mass. So mass has been taken out, okay. That is the reason you do not see m explicitly over here, and that is the reason I alerted you to the fact that keep track of the dimensions, because in some of the books you will read obviously E equal to mv square by 2, which is the kinetic energy, right, and then the potential energy will be kappa over r having the dimensions of ml square T to the minus 2, and that will give you a different dimension for kappa, right. So keep track of that. So this is what is called as specific mechanical energy, which is energy per unit mass. So rather than the energy itself, I will be dealing with what I shall refer to as the specific mechanical energy, and those who do rocket science, this is a more common term to use. How did we get it? We started with the equation of motion, we just played with it, we just did algebra, we took the projection of the equation of motion on the velocity, right, and then we did calculus, we did integration, and from the integration we discovered a conserved quantity, namely the energy. So essentially we got the conservation of energy from the equation of motion, okay. We also see that as we arrived at this conservation principle, which is the conservation of energy, it is the integration with respect to time and differentiation with respect to time, which are inverse processes, these were intrinsically built into our analysis, and this should remind us that here we are meeting a conservation principle, which obviously comes from the fact that the derivative of this energy with respect to time goes to 0, and there is a symmetry with respect to temporal evolution, that as time changes, okay, from yesterday to today to tomorrow, or from T1 to T2, right, the law has not changed. So there is a symmetry with respect to invariance with respect to time, and it is this symmetry which is connected with the conservation principle. So this is a theme that we have carried in our discussion in some of these units, especially in unit 1 and now again in unit 4, that there is an intimate connection between symmetry and conservation laws. And here we see that by doing this integration with respect to time, we discover the law of conservation of energy, and we have actually deduced it from the equation of motion by just doing algebra. Okay. All we did was to take the projection of the equation of motion on the velocity and then integrated this. So now let us see if this method really works. Can we get other conservation laws just by playing with the equation of motion? Okay. So here look at the equation of motion again, we have the equation of motion. We had taken in the previous case the dot product of the equation of motion with velocity, which is what led us to a conserved quantity, namely the specific mechanical energy. And we saw this in the context of the connection between symmetry and conservation law, and in the context of the Lagrangian or the Hamiltonian formulations that we discussed in unit 1, we recognize that the conserved quantity energy is canonically conjugate to the variable t, which really does not appear in the Lagrangian. Okay? So, there is a symmetry with respect to time, and that results in the conservation of energy. Now, instead of taking the dot product, let us take the cross product. Let us just play with it. We have got the equation of motion, and by taking the cross product, we will find yet another conservation law. Okay? Now, this is a wonderful technique. So, all we have done here is to take the cross product not with velocity, but with the position vector. Okay? In the previous case, we constructed the scalar product, the dot product with the velocity. Now, we take the position vector and compose the cross product with the equation of motion. So, equation of motion has got two terms. I take the cross product of each of those terms with the position vector and get a vector equation. Okay? Now, if you see the second term, this is the cross product of r with r. So, cross product of two collinear vectors will vanish, which means that the first term vanishes. So, r cross the acceleration, this will go to 0, right. Acceleration is of course along the direction of the force, right, and this comes because the force has got a radial symmetry. Okay, so, there is a symmetry which has become manifest. Okay, these are the beautiful things in physics, that the symmetry of the force becomes manifest in this particular context, that the force is a radial force, we knew it, but we see that as a result of this we are going to discover another conserved quantity. So, we have got the cross product of the position vector with the acceleration, which becomes a null vector. Now, we use a simple algebraic identity, which is the time derivative of a cross product of position and the velocity vector will be the time derivative of the first vector, its cross product with the second vector, plus the first vector and the cross product with the time derivative of the second vector. So, this is just an identity that we have made use of, out of which this obviously vanishes, because this is a cross product of velocity with itself, and now you have got this, which is the same thing as the force being radial. So, this is the identity which is completely consistent with the fact that the force is a radial vector. Now, if this is true, okay, then the r cross velocity, if the time derivative of the position vector and this is the time derivative of a cross product, right. This is the cross product of what? This is the cross product of the position vector r with the velocity r dot. The time derivative of the cross product of the position and velocity, this time derivative goes to 0, okay. And if a time derivative of any quantity goes to 0, then that quantity is conserved, right. So, the cross product of position and velocity is a constant of motion, and that is angular momentum. Rather, it is a specific angular momentum. Angular momentum is r cross p. P is momentum, mass times velocity, but we are developing these equations in units of mass, right. So, angular momentum is r cross p, the specific angular momentum is r cross v. Okay. So, the specific angular momentum is conserved. If you multiply this by mass, you have the conservation of angular momentum, right. So, angular momentum conservation has come again from the equation of motion by simply composing its cross product with the position vector and doing simple algebra. Okay. This is really very interesting. Mind you, we are dealing with the specific angular momentum rather than the angular momentum itself. So, once again we meet a connection between conservation and symmetry. The quantity which is conserved is the angular momentum or the specific angular momentum, which is the same. The symmetry is a radial or the central fold symmetry of the force. So, that is this connection between symmetry and conservation law that we meet again. On this we discussed at some length in unit 1 that the homogeneity of time, temporal evolution, if it leads to homogeneous equations of motion which do not change with time, then you get the conservation of energy. Homogeneity of space, in which translational symmetry is involved, it leads to conservation of linear momentum. Isotropy of space, in which there is rotational symmetry, central field symmetry, you get conservation of angular momentum, and this is the essential content of the Noether's theorem, which we discussed in unit 1 to some extent. Now, let me remind you, because it is a very important feature, that the invariance of the Lagrangian with respect to time in the Lagrangian and Hamiltonian formulation led to the conservation of energy. Likewise, if you consider displacements in space, this again we discussed at some length in unit 1. So, I will not spend any time in discussing this in any further detail, but I will just remind you, we have seen these slides and these equations in unit 1. So, I will not spend much time on that. I will just remind you that because the space is homogeneous, from the Lagrange's equation you find that the conservation of momentum comes from the homogeneity of space. We also studied in unit 1 that if you consider virtual displacements of a system of particles which is interacting within itself, then the net virtual work done is 0, and if this displacement is arbitrary, then the sum of these internal forces must vanish, and that led us to recognizing that the linear momentum is a conserved quantity, which again comes from the homogeneity of space. So, this came from, this is the discovery of Newton's third law. Instead of learning it as a law of nature, we could actually get it from the properties of translational invariance in homogeneous space. And we discussed this possibility that given the symmetry related to translation in homogeneous space, could we have discovered Newton's third law, and the answer of course is yes. So, this is one way of getting to the, we have discussed how to get conservation principles from the equation of motion, for which you need the law of nature, you need the physical law. So, given the physical law, you find what the conservation principles are, what quantities are conserved, or you could ask, if you know what quantities are conserved, how would you find the law of nature, what is the physical law. So, this question is very nicely framed in this particular fashion. Are the conservation principles consequences of the laws of nature, or are the laws of nature the consequences of the symmetry principles that govern them? Okay. And the thinking in the physics community sort of changed with Einstein. Okay. Until Einstein came up with the special theory of relativity, one believed that the conservation principles are the results of the laws of nature, which is what we did in the previous two cases, right. We began with the equation of motion, and from that we deduced the laws of, we deduced what quantities are conserved. But since Einstein, physicists began to look at the conservation principles as consequences of the underlying symmetries, and using this connection they learned to discover what are the physical laws which govern them. So, this suggests a recipe of discovering laws of nature, which is one of the primary goals of physics. So, I illustrated this in the case of the Newton's third law, which we did in some details in unit 1, but we quickly recapitulated that we deduced Newton's third law from symmetry and invariance rather than the other way around. On this approach, it places symmetry ahead of the laws of nature, and the people who contributed to this thought process, of course, the thinking began with Einstein, and this is contained in a very famous theorem known as the North Theorem, and we owe it to Eugene Wigner, who really very lucidly illustrated these ideas using group theoretical methods, but those are obviously beyond the scope of this course. So, now let us play with the equation of motion a little bit further, because we have already discovered some very nice features out of it. Now, we have the specific angular momentum, which is a conserved quantity, and now what we will do is construct the cross product of the specific angular momentum with the equation of motion. Again, we are just playing with the equation of motion. Okay. We began with the equation of motion, took its projection of the velocity, got the conservation of energy. Then we began with the equation of motion, took the cross product with the position vector, we discovered the conservation of energy, conservation of angular momentum, right. Now, we begin once again with the conservation of, we begin with the equation of motion, and now we construct the cross product of the equation of motion with the specific angular momentum and ask ourselves, is this going to lead to any new conserved quantity, and if it does, what is the associated symmetry, right. That is the question that we will now address, because we have become used to the fact that if there is a conserved quantity, there will be an associated symmetry and vice versa. We have also got used to the idea that given the equation of motion, by playing with it we can discover new conserved quantities. So, if we play some more and now we think about constructing the cross product of the equation of motion with h, which is the specific angular momentum, will it lead us to another conserved quantity? Maybe yes, maybe no, let us do this and find out. But let us also keep this in mind at the back of our mind, that if we do run into another quantity, conserved quantity, what kind of symmetry will we associate with this? That is another question that we shall need to deal with. So, let us construct the cross product of the equation of motion. So, this is the equation of motion now. Okay. We construct the cross product of this equation of motion with the specific angular momentum, which I write as h. So, h cross r double dot is the first term, and h cross r multiplied by this kappa over r cube coming from the second term equal to a null vector is the result that we get. Now, this is just algebra, this is the vector algebra. So, this is what we have got. We have composed the cross product of the equation of motion with the specific angular momentum. Okay. H itself, I have only used the definition of h, which is angular momentum, rather the specific angular momentum, which is r cross v. So, I have rewritten this, instead of h I have used r cross v over here, and now I have got a cross product of r cross v with another vector r cross v cross r. So, this is the famous back cab rule, as some of you call it, right, and you can expand this cross product in which there are 3 vectors, and this cross product will give you the r dot r coming from the outer product, and this is the one which is in the middle, which comes here, minus the dot product of this outer vector with the adjacent vector, which is r dot v, times the remote vector, which is r, right. So, this is the famous back cab rule which I have used over here, and I have simply rewritten this after expanding this vector product. Now, what we need is this r dot v. R dot r of course is r square, so that we already know. We need r dot v. So, let us determine this. V is the time derivative of the position vector, which is the magnitude times the direction, okay, and this will be r r dot, as we have seen in the previous case. So, this is the r r dot dr by dt, right, which is the rate of change of the magnitude of the position vector. So, now what if you combine these results, you have h cross acceleration coming from the first term, and in the second term you have kappa over r cube, and what you have in this bracket is r square v minus r dot v is this r r dot and this position vector r. So, this is just a simplification of this algebraic relationship that we have been dealing with. So far so good. Let us play with this further. We recognize the fact that if you take the time derivative of this cross product of h with v, okay, this will give you dh by dt cross v plus h cross dv by dt, right. The d by dt of h cross v will give you dh by dt cross v plus h cross dv by dt, but dh by dt is the rate of change of the angular momentum, and we already know that the angular momentum is conserved. So, dh by dt will vanish. So, you have the second term which should go to 0. So, you get the time derivative of h cross velocity, which must be equal to h cross r double dot, right, and this is the quantity which is appearing in the first term over here. So, for the first term we can write the time derivative of h cross v. So, for the first term I have written the time derivative of h cross v, the remaining terms I have written as they are, right, and the whole thing equal to 0. But here I now take this 1 over r cube inside this bracket. So, r square over r cube gives me 1 over r. So, the first term becomes v over r, and the second term gives me r dot over r square, because this r square will cancel r square. So, that will give me only 1 over r, but then there is a unit vector over here. So, I write it as r over r square. Okay. Remember that all we have done is to use the equation of motion, played with it, we have taken the cross product with the specific angular momentum, everything else is a consequence of the vector algebra. No new principles inserted in our analysis. So, now what have we got? If you look at this quantity here, okay, v over r minus r dot over r square, this is nothing but the derivative of this unit vector, because this is the derivative of a ratio. So, it is 1 over r times dr by dt, 1 over r times the rate of change of the position vector, which is velocity over r, and then minus the position vector times the derivative of 1 over r, which is minus 1 over r square, which is what you see over here. So, this second term can be easily seen as the derivative of this unit vector, and having recognized this, we notice that the two terms both involve time derivatives, and you can write this as a common differential operator time derivative of the first term, which is h cross v, plus kappa times this unit vector, and what you have is a conserved quantity, because the quantity in this bracket must be conserved since its time derivative vanishes. Do you see how we got a conserved quantity? We began with the equation of motion, played with it, did some algebra. When we did it by taking the projection of the equation of motion on the velocity, we discovered the conservation of energy. When we constructed the cross product of the equation of motion with the position vector, we discovered the conservation of angular momentum, right. Conservation of energy we know is associated with symmetry with respect to time evolution. Conservation of angular momentum or specific angular momentum we know is connected with the central field symmetry or the rotational symmetry. And now we have discovered that by composing the cross product of the equation of motion with the specific angular momentum, we have discovered that d by dt of this quantity in the square bracket goes to 0, which means that the quantity in the square bracket is constant, and therefore we have discovered a conserved quantity. It does not look like energy, does not look like angular momentum. What is it? It is a new physical quantity which is conserved, right. So, this is the conclusion that we get, that the time derivative of this combination of vectors goes to 0, which means that the vector inside the square bracket is a constant. It is equal to some constant vector, and I call this constant vector as minus a. It does not matter, that minus sign has got no specific meaning, you can always write it as b and say that that is a constant vector, and then define an a which is negative of that, it does not matter, right. Minus a is as constant as a itself, because minus 1 does not change in physics, right, as best as I know. So, here we go, we have discovered a conservation principle. It is not one of the usual conserved quantities, it is not energy, obviously it is not angular momentum. This is a new conserved quantity which we have arrived at, and we have arrived at simply by playing with the equation of motion. This quantity is called as the Laplace-Runge-Lenz vector. Okay. The name, it has got a very nice name, this is the Laplace-Runge-Lenz vector, and depending on what book you are reading, you might read this differently. Instead of v cross h, you might read it as p cross l, where p is the linear momentum and L is the angular momentum, but mind you, I am developing it in terms of the specific mechanical energy, the specific angular momentum, right. So, the mass does not appear in this, but it is the same vector, it is the same physics. Okay. So, this quantity is called as the Laplace-Runge-Lenz vector, and this is the definition of the Laplace-Runge-Lenz vector. It is v cross h in the units in which we are developing this algebra. V cross h minus kappa times 0, this is a constant of motion, it is a conserved quantity, and we have discovered a constant of motion yet again by just playing with the equation of motion. I want to remind you that the dimensions of kappa are L cube t to the minus 2, the dimension of v cross h will be L cube t to the minus 2, because if you see p cross L, you will have different dimensions obviously. Okay. Now, we will take a break at this point. If there is any question, I will be happy to answer, and we will continue from this point in the next class. So these are some references which I will like to bring to your attention. There is a very nice book by Montenbroek and Gill on satellite orbits, models, methods and applications that you might want to read. Francis Hale has got a book on Introduction to Space Flight, and you might want to read that book. And we will take a break, and after this in the next class we will discuss the dynamical symmetry of the Kepler problem, because we have discovered a conservation principle. Now we must ask, what is the associated symmetry? When we discovered the conservation of energy, we knew that the symmetry involved was symmetry with respect to temporal evolution, changes in time, translation along the time axis. When we ran into conservation of angular momentum h, the specific angular momentum, we associated it with the central field symmetry, with the rotational symmetry. Now we have run into a new quantity which is conserved, namely the conservation of the Laplace-Runge-Lenz vector, which is a constant quantity, and we must ask what is the associated symmetry. So we will discuss this question in the next class. Thank you for now.